Okay, so let's begin up with our first oral presentation. So let's welcome Nihal, Naveen, Shetty on the stage.
Very warm welcome to everyone present over here. I'm Shetty Nihal Naveen. I hail from Sahyadri College of Engineering and Management from Bangalore. I'm a final year undergraduate student. It's a privilege and both an honor to be here and presenting my research over here in front of such an esteemed audience. Now, introducing my framework. It's basically called Quantum Inspired Local Tensor Regression Framework, and it sits at the intersection of quantum information geometry derived from the quantum Fisher information matrix and classical and statistical machine learning. The key objective of QLTR is to explore a quantum inspired weighting mechanism for local tensor regression. The central idea is to use the Buress distance, which is derived from quantum Fisher information, to weight local learning problems in geometrically meaningful way. Now, on the theoretical front, we have reformulated the regression on a Riemannian manifold, making curvature explicit. We show that the QLTR update rule behaves equivalently to natural gradient descent, even though we never compute or invert the Fisher matrix. We also provide proof of local geodesic convexity, power law stability, and polynomial time solvability under dual constraints. On the empirical front, even though we have achieved modest results, it's due to the theoretical and practical research gaps. QLTR achieves improvements of up to 4.92% across synthetic datasets and a statistically significant 1.22% improvement on the QM9 molecular dataset. The key takeaway is that quantum geometry is not just conceptually elegant, it offers real computational advantages. Now, what were the key research challenges that we had encountered on the way? The fundamental challenge that we address is modeling non-stationarity multilinear systems. In many scientific domains, including quantum chemistry, material sciences, and econometrics, the relationship between variables changes across the input space. Traditional global regression models fails in such settings. The response tensor is defined as the order of k. When the k increases, the number of parameters grows exponentially. This is the well-known curse of dimensionality. QLTR tackles this by encoding inputs as a low-dimensional quantum states, weighting each sample using the Buress distance, and fitting a locally adaptive low-rank tensor model. Now, we have been through a lot of iterations, and the optimal dimension states that we got was d is equal to 5. And the central hypothesis is that the driving work is Buress distance weighted regression enables superior optimization mirroring natural gradient descent. Now, with this in mind, let us explore the geometric foundations that enable QLTR. Now that we have established what the problem is and what the traditional approaches fail, I want to introduce a geometric foundation that makes QLTR fundamentally different. This is where the elegance of the approach truly becomes visible. The QLTR framework lives simultaneously in two mathematical worlds, and understanding these worlds is essentially for appreciating why the method works. The first space is the manifold of quantum state. A quantum state denoted P is a positive semi-definite matrix with unit trace. Unlike ordinary probability vectors, these matrices live in curved geometric space. Distances here are not Euclidean. They reflect how easy or hard it is to distinguish one quantum state from another. This leads us to the quantum of quantum fidelity. This expression essentially measures the overlap between two quantum states. From fidelity, we construct the Buress distance. Now, the Buress distance is basically introduced in the quantum Fisher information theory. It tries to introduce how one data point is significant to other, relatively significant to other data point in a quantum space geometry. Now, the moment we introduce Buress distance, we automatically introduce curvature into our learning process, because this distance is directly connected to the quantum Fisher information, which measures how sensitive a quantum system is to perturbations. This sensitivity is a form of curvature. It tells us how the space bends. Using Buress distance for weighting is equivalent to allowing the geometry of information itself to influence learning. The second space where QLTR operates is the manifold of low-rank tensor. Traditional tensor regression quickly becomes computationally intractable because the number of parameters grow exponentially. Now here, to address this, we restrict our regression model to a Tucker low-rank representation. This restriction does not simplify the model arbitrarily. It basically places a lower dimensional smooth manifold with well-defined tangent space where every update during optimization lies within this tangent space. However, Tucker decompositions are not unique. Multiple parameterizations can represent the same tensor. For this reason, we impose gauge fixing constraints which eliminate redundant degrees of freedom and ensure uniqueness of representation. Without this step, optimization would be ill-posed with gradients drifting in meaningless directions. Now, when these two geometric spaces interact, quantum state manifolds shaping local weighting and tensor manifolds shaping the local representation. We obtain a learning framework that basically is both expressive and mathematically grounded. With this geometric foundation in place, we can now examine how QLTR formulates its optimization problem. Having seen the geometric basis, let me now walk you through the QLTR optimization objective. This is the core of the model and one of the main reasons the method works so effectively. The idea is to learn a localized tensor representation centered around some point C. C is the input space. Instead of treating every training example the same way, QLTR assigns a weight to each example based on how close its quantum embedding is to the embedding of the center. And this closeness is determined by the Buras distance. The optimization problem is written as the standard update over there. Now here the weight assigned to each sample is exponentially weighting ensure that sample closest to the center in the information geometry. While samples far away have exponentially diminishing impact. Now comes the most remarkable property of QLTR. Even though the optimization looks like a standard weighted regression over here, the structure of the weights implicitly transforms the update direction. The loss structure of the weight implicitly transforms the update direction in such a way that the surface becomes curved in a specific descent that is determined by the Buras metric over here. Because of this curvature, the gradient descent updates as if we are performing a natural gradient descent over here, which is a steepened descent in the direction on a curved manifold. Now, how to know whether the natural gradient descent is known to be more stable and efficient than any ordinary gradient descent? It typically requires more computation from the Fisher information matrix, which is expensive, obviously. The QLTR avoids this cost entirely. What we have introduced over here is a Buras-induced weighting, which automatically embeds curvature into the loss. So we recap the benefits of natural gradient behavior over here without ever computing a Fisher matrix. Now, this leads to improved stability, smoother optimization trajectories, and faster convergence in a non-stationary region. Now, this introduces our first theorem over here, which provides a rigorous convergence guarantee for QLTR. Now, under standard smoothness assumption, we show that the sequence estimates approaches the optimal solution over here with the following contraction, which is visible over there. The learning rate with this inequality expresses is that the distance between successive iterations decreases multiplicatively. Now, this is a classical form of geometrical convergence over there. Now, why is QLTR faster than Euclidean tensor regression basically? The answer again lies in the geometry. The Buras distance weighting effectively introduces a Euclidean curvature aware preconditioning in regions of the loss landscape where condition QLTR automatically adjusts its update to follow a better condition direction. Now, this adaptivity leads to a faster convergence, particularly in non-stationary components. With convergence being established, let's now discuss whether we can actually compute QLTR in practice. One reasonable concern when hearing all of this geometry and tensor algebra is whether the method is tractable. Fortunately, this theorem establishes that QLTR is computationally feasible. Now, the computational complexity of the method, at first glance, this might seem a bit daunting, but the crucial idea is the dual constraint strategy that we have been being imposed over here. The constraints are the tensor operation that would normally cause exponentially scaling now operates in a controlled polynomial time regime. The main computational cost becomes SVD operations and ALS updates, both of which are well optimized and numerically stable. This QLTR is not only theoretically appealing, it is computationally practical as well. Now let us examine how it performs in controlled experiments. Now, while we perform our empirical validation, in the synthetic experiments we tested QLTR across 5 challenging scenarios. The first one being high non-stationarity, ill conditioning, outlier contamination, mixed noise regimes, and structured distortions. Each scenario was tested over 500 independent trials to ensure statistical robustness. Now, QLTR consistently outperformed both the Euclidean regression and classical tensor regression models. The improvements reached up to 4.92%, which is modest in nature, but it's quite significant. That's why the real value lies in the robustness for it. When we examine the Weylian plots, we see that the QLTR does not just improve accuracy, it dramatically reduces variance. The distribution under QLTR are tighter and more stable. This means the model is less sensitive to noise and less fragile to perturbations. The result indicates that incorporating curvature through Buras distance has a measure of stabilizing effect on learning. Now, to better understand the behavior, we performed ablation studies as well to validate our design. The ablation studies gives us insight into why QLTR behaves the way it does. Now, the first ablation concerns the quantum bandwidth. When bandwidth is too small, the model becomes overly sensitive. When it's too large, the model becomes too smooth and loses the local structure. But in the middle range, the performance is optimal. This reflects a balance between local relevance and stability. Now, the second ablation concerns the quantum dimension. Increasing the quantum dimension adds expressive capacity but also increases computational cost. However, accuracy remains remarkably stable across dimensions. This shows that even small quantum embeddings carry sufficient geometric information. The third ablation concerns feature scaling. The stability of the model changes significantly with scaling, confirming that quantum geometry reacts intensively to representation. This sensitivity is not a weakness, but it's a signal that curvature matters. Across all the ablations, one pattern is clear: QLTR behaves predictably and logically in response to meaningful geometric changes. Now let's turn to the real validation, where we have tested QLTR on QM9 quantum chemistry datasets. Now, in the QM9 dataset, which contains 130,000 molecules and 19 regression targets, QLTR again showed measurable improvements, but the improvement was quite very modest in this nature. The improvement in accuracy was 1.22%, relevant to the Euclidean tensor regression. While the number may appear small to you in molecular property prediction, even a 1% improvement can correspond to meaningful chemical insight or better predictive reliability. So now importantly, the variance reduction was substantial. QLTR eliminated many of the extreme outliers that the Euclidean regression produce. The box plots shows narrower interquartile ranges and shorter whiskers, confirming that QLTR produces more consistent predictions over here. The reason QLTR does not well behave here is intuitive, because when we started the empirical validation, due to SVD initialization, the ALS convergence happened within 1 or 2 iterations. So the accuracy, like the performance, might not occur instantly because of the fast convergence over here. So one of our theorems might hold invalid in practicality. So that might take more future work in case. Now here you can see, in practice we observe that the convergence speed is similar to that of Euclidean tensor regression, but there are 3 key reasons for this. First, SVD initialization is extremely effective and places the model already close to the optimum solution. Second, ALS updates are naturally stable and converge more quickly. Third, the synthetic settings often involve low noise, where curvature differences do not strongly influence the optimization trajectory. Thus, although the theoretical results guarantee stability and robustness, the practical convergence behavior is dominated by the optimizer rather than the geometry. Now let's dive into the computational complexity and the synthesis of QLTR. When synthesizing both the theoretical and empirical perspective, QLTR shows a consistent pattern over here. Now, theoretically, QLTR is a polynomial time curvature aware and stable. Empirically, it behaves precisely as theory predicts, but the runtime matches analytical expectations. It avoids catastrophic failures commonly seen in analytical expectations. The improvements of 4.92% in synthetic datasets and 1.22% in QM9 align exactly with what information geometry would suggest. In summary, QLTR's behavior is predictable, reliable, and grounded in its geometric foundation. Now, diving on the discussion and implications part of it, this work leads to several important insights. The first insight is that theoretical advantages in curvature-aware optimization matters most when the data is noisy and highly non-stationary. In smoother settings, classical optimizers like ALS dominates regularly. The second insight is that QLTR has limitations. SVD becomes a bottleneck at very large scales. The choice of lower Tucker rank matters, and feature scaling plays a crucial role in that. The fourth insight is that the quantum-inspired geometry has immense potential in scientific machine learning, particularly in chemistry, material sciences, and physics-informed modeling. Now, to conclude about my paper, to summarize, this work makes theoretical contributions such as the convergence guarantees, polynomial time solvability, and natural gradient-like behavior without the Fisher matrix computation. Empirically, the framework improves synthetic performance by 4.92% and real-world molecular performance by 1 to 2%, while providing robust low-variance predictions. Looking ahead, exciting directions include quantum-inspired input encodings, adaptive rank tensor models, and new applications in chemical discovery and material designs. The overarching message is clear. Quantum geometry is not just elegant, it's computationally powerful as well. And I would like to thank my co-authors over here. Thank you.
Questions?
Yeah, nice presentation.
Thank you.
Can you tell me about the physical interpretation of the gauge fixing criteria you were showing on the second or the third slide?
Yeah. Over here.
Yeah, this constraint. So what physical interpretation of the gauge fixing condition here?
Basically, the initial intuition was we had to convert the data points into quantum states as well. So therein we got to realize that gauge fixing constraints are required in this field. That's why we had to integrate that possible interpretation over here. The fixing condition is set to 0 to ensure uniqueness on the tangent bundle. So basically, we are even including a bounded tangent scaling so that when we expose it to the quantum states, the outlier robustness is not lost in the procedure. So as to that perspective, we have done this.
Okay, thank you.
Thank you.
Okay, thank you so much.
Thank you.
Up next, we will move to our next Lokesh Reddy from TCS Research. Please, a round of applause for Lokesh.
Good afternoon, everyone. This is Lokesh from TCS Research, and I will present my work on RENN, a framework for unsupervised denoising. Yeah. So there is a lot of talk about rapid sensorization in various industries. So the consensus is quite clear. We need massive amounts of data to train our models and to build accurate digital twins. Yeah. Okay. Yeah. So I was saying we need massive amounts of data to train our models and build accurate digital twins. But however, the ground reality is quite different. The sensor data is inherently, it's corrupted, it's noisy. So as a result of this, if we train our models on such a noisy and faulty data, we cannot utilize the full power of our sophisticated models. So what's the solution to that? We need to find, before using the sensor data, we need to have a technique, a tool, which can correct this faulty data. So let's understand through this simple reactor diagram here. So we have the sensors tell us that we have an incoming stream of 100 tons and an outgoing stream of 110 tons. Now for a steady state system, we know that this is physically impossible. Yeah, so this inherently violates the fundamental physics. So the next question is, can we ignore this discrepancy? Is it too much? Can it affect the 10 tons per hour discrepancy? Can it affect our industry so much that we should not ignore it? So the answer to that is in this figure on the right. So you will find that the mass balance is at the center of every other of any industry. So if the central mass balance is faulty, the errors will cascade to every other part of the system. So what do? We reconcile the data by setting up an optimization problem where we try to minimize the adjustments by making it satisfy the underlying physics while minimizing the adjustment error. Now on paper it sounds simple, but in reality it is very tough. Now why? I have listed the three main reasons for that. The first is the nature of the data itself. Now, high frequency noise, the sensors not only contains measurement noise, but also large systematic biases, which are called gross errors. And then we have the second one, which is more of a practical challenge. Now, since sensors are very expensive, we cannot place sensors throughout the industry. And then we have the third challenge, which is related to the method being implemented here. Now, in actual scenarios, we will never have the access to the real ground truth data. So if our model relies on the true values for training, that will never happen, as we don't have access to it. And the second reason is, if there is an error in any part of the network, it will eventually propagate to other parts as well, if there is a considerable time delay in rectifying it. So we need a real-time correction in data reconciliation. Yeah, so now all the existing methods can be categorized into these three types: Lagrange multipliers based, robust estimators, and the data-driven models. So each method has its own pros and cons, but none of them addresses the reconciliation problem holistically. Now, for example, let's say the neural network methods. Now, these networks are very fast and it can be robust, but they do not, they rely, first of all, they rely on true values for training, and then they do not account the underlying physics in their learning. So to close this gap, we propose the RENN, which is the robust estimator guided neural network, which integrates the quasi-weighted least squares function into the standard pin architecture. Yeah, so before moving on to the methodology, I just wanted to show why we chose QWLS for this. From the graphs here, you can see that you can see the problem of the standard L2 loss. As the error increases, the penalty term grows quadratically, which means that if the sensor has a larger gross error, it will not only affect its own measurement, but also it will smear its error on other measurements which are probably good. Compare that to the QWLS, where it sees a large error and it detects and identifies that, okay, this is a large error, it must be an outlier, therefore I should give less importance to that particular measurement. Now, these are some mathematical equations which describe this robustness behavior, like mathematically. Yeah. So before designing the actual network, so it is a standard practice to scale our inputs. So for that, we have used min-max scaling to compress our measurements, which are the inputs, and then the outputs, the network estimates, and then the sensor precision or the standard deviation. Since you cannot plug scaled variables into an unscaled physics, so we also need to non-dimensionalize all the equations which are involved in our system. So here we have mainly two kinds of equations. The first is the set of process constraints, which are mass balance equations. And the second one is the QWLS objective function itself. Yeah, so this brings us to the core of our training process, which is the composite loss function we designed. So we designed the network to basically do two things simultaneously. The first is it must respect the sensor data through our reconciliation specific loss. And second, it must obey the underlying physics, which is done through the constraint loss. Now, if you see the reconciliation loss, so that's where we implement our QWLS equation. Now, the key takeaway from this slide is you will not find the X2 term anywhere in the loss formulations, which proves that the method is fully unsupervised. Yeah, now that we have our data ready, we have scaled it, and we also have our loss functions formulated. Let's see how these are integrated into the pin architecture. So from the left, we have our sensor measurements coming in. It goes to a standard pre-processing block. Then we have the network, and then we get the network estimates. Now, the function of point, all the network estimates coming at a given point of time are indexed together. So this is done to avoid cross-sampling between two sets of data at two different times. So why this is necessary? It's necessary because while sampling the collocation points for loss evaluation, we have to sample the correct points and not between different sets, different times. So basically for that, point cloud is implemented here. And once we have the correct sampling points, we evaluate our two losses, the reconciliation loss and the constraint loss, then we back propagate it. Yeah. So now that our model is ready to be trained, let's see how to evaluate our model. So the reconciliation problem has has different challenges. We have chosen different metrics, each with its own purpose. So for accuracy, we have chosen R-square, the coefficient of determination. To quantify the error reduction, we have chosen the RMSE. To show the physics consistency, we have used mass balance closure rate. And then to compare with other existing methods, we have chosen the relative error reduction. Yeah. So we have validated our model on different benchmarks, but I will discuss the results just for the stream metering system. And I will show this summary for a couple other benchmarks. Yeah, now let's get to the results. So this graph is a parity plot between the normalized reconciled estimates or the network outputs and the normalized ground truth. Now you can see that all the data points cling tightly to the, to the diagonal line, and we can see that there is a good sharp linear alignment. And I've also reported the stream-wise R-square range. For the stream metering system, it is 0.91 to 0.99. And if you see the benchmarks, so our most complex system which we solved is the ethylene separation plant, which has 26 units and 50 streams. And even for the complex systems, the lowest R-square observed is 0.87. So we can confidently say that the model is reconstructing the true process state, even when there is a wide variation between the individual flow rates. Yeah. So here we further break down the error stream by stream. So you can see the red dots, which are the errors in the original measurements coming from the sensors, and then the green ones are the errors in the network predictions. And the lines connecting the red and the green is the magnitude of correction. So from the plot, it is quite clear that our model corrects very large errors, but it's not just limited to correcting large errors. It is also identifying those which already has smaller errors, which means the sensor is already good enough, the measurements are already good enough, but our model also refines the already plausible measurements. Yeah. So the most important aspect of a reconciliation method is that it should obey the physics. So for that, we have shown two heat maps, one corresponding to the measurements and the other the network predictions. Now, if you check out the heat map for the measurements, you will see a non-uniform color distribution across the process units, which shows that there is a significant residual. But for the RENN predictions, you will see that it is a single gray uniform color, which is close to very zero across the process units. Now, for the stream metering system, the lowest closure rate observed in a process unit is 99.75%, while the majority of them had a closure rate of above 99.9%. Yeah, for comparison purposes, we have chosen several traditional estimators, a baseline supervised ANN trained on true values, and the QWLS itself. Now, in all of the benchmarks, you can see that the RENN consistently achieves one of the highest mean RER and is at par with the QWLS. And notably, the ANN, despite being trained on true values, performed poorly. This shows why the integration of both the physics constraints and the reconciliation specific laws is important. Finally, we wanted to test the effect of each component in our system. So we removed every component and then tracked the mean RER percentage to see how the performance varies. So if you see the blue line, which is the full model having every component and the tuned weights has the maximum RER, while if we drop even if a single component, the performance degrades. And the most important of them all is the reconciliation specific loss. If we remove the reconciliation specific loss, then the degradation is very severe. It is negative, which means that the model actually introduced more errors rather than rectifying it. So to conclude, I will summarize by stating that our model was effective in addressing all the challenges of the industrial data reconciliation. So first, our model could successfully predict the true process state without ever needing the true values. And then since we are embedding the process constraints into the learning, so the physics is a guarantee. It always satisfies this physics. You can see from the closure rate, which is above 99%. And then since it is a neural network, it is very fast once it is trained. So it is applicable for real-time applications as well. So I would finally like to take this opportunity to thank our CTO, Dr. Harik Win, and our research head, Dr. Sachin Lodha, and a special thanks to CSML organizers for arranging this wonderful conference, and also the ARIX Labs and the ISC as well. So with this, I end my talk here, and I would be happy to take any questions you have. Thank you.
So any questions?
So in this, hello? So you start with the assumption that you know the physics of the problem. There could be situations where the physics could be so complicated that you may not be fully aware of all the physics. So how do you address that challenge? And the part B of discussion, part B would be like you have sensors to begin with, they are working fine, but as time progresses, sensors start drifting. So how do you address that challenge?
Yeah.
Thank you.
Yeah, so the first question is, so yes, it is correct. We are assuming that we know the physics exactly. If the physics changes, then the model will obviously give wrong results. So in the literature, there are quite a few methods which use kind of modular or hybrid methods which they simultaneously use the known physics, which is known to us, and also they collect the data and they use the data part as well. So it's a part of system identification as well. So we identify the system from the data and use the physics as well. So it is a modular kind of thing. So that addresses it. I will not say it will completely address the problem, but to some extent. And then coming to the second question. So yeah, we have drift, we have miscalibration, we have sensor erosion, due to which it will always give a systematic bias. So those are actually called the gross errors. So the noise is actually two types. First one is the random noise, and then the gross errors. So the random noise is already there. You cannot, it is inevitable. You cannot remove that from the sensors. And the gross errors, it is there. So that's why we have used the QWLS. Now the gross error is always a constant error. The magnitude and the sign is always constant. It doesn't matter how many experiments you repeat. It will always give a certain, it is fixed. So the QWLS actually addresses that. So how? It lies in the behavior of the QWLS. So if it encounters a larger error, let's say here you can see, right? It goes from -10 to 10. So if we take the 10, then it says that the error is very large here, which it should not be. It is not obeying the random distribution. Therefore, it will treat it as an outlier, and it will reject that measurement. So that's how the gross errors are actually treated in this.
The situation when your sensor maybe fails
Yes.
suddenly, but there could be situation where, say, a sensor which is supposed to measure a temperature, it is measuring temperature 100, and slowly over time it starts to measure 99.9, 99.8, and slowly
It
drifts
degrades.
away from the actual value that is there. So then this would not record it as a large error, I guess, right?
Yeah, so there is a limit. After a certain point of time, it will record it, but before that, it will treat it as a normal noise.
Yeah. So,
Yeah.
but that time could be very long. So that's what.
Yeah, so if we consider a smaller error, then there is no problem. It will treat it as a random noise. It will correct the estimate, but we will not know that the sensor is degraded. So that's the only disadvantage in that. But the measurement will be fine.
Okay. My name is Dheeraj. I am from IIIT DM Kanchipuram. So mine is a simple doubt actually. Correct me if I'm wrong. So this is an unsupervised learning model, right?
Yes.
But you have selected accuracy as your metric, right? So from what I understood, it's usually used in supervised learning. So how have you altered it for unsupervised learning?
So that is for just evaluation purposes. After the training is done, we are predicting the estimates, and then we are validating it whether it matches to the true values or not. So we have not used true values in the training part anywhere. So this is just to show that the model works.
So actually, so have you modified it or the same equations?
No, it's the same equations.
Same equation.
Yeah. Now, since we generated the data ourselves, we have the true values for that.
Any other questions? Okay. So
Thank you.
thank you.